He has been working on this new product together with Thomas, who also was at EMPA before. And I will give you my mic.
Thank you for being here at this multidisciplinary seminar. Our presentation will be presented by my former EMPA colleague, Dr. Wakili, and me. First, I want to show you the properties, main ingredients, and some material parameters of the aerogel render. After this, I will show you some slides from the monitoring of the historical mill in Sissach. We have made the experience that people from monument preservation, like Mr. Niederberger, are very interested in ingredients. So you can see here the main ingredients of the aerogel render. This is hydraulic lime and hydrated lime, and a small amount of white cement to ensure the compactness in an early state of the binding process. Then the aerogel. This is amorphous silica, and it's well known since more than 80 years, and it's absolutely not dangerous. Then some other mineral aggregates like expanded perlite for the weight reduction of the product. And then the last three ones are typical additives to improve the workability of such a product. The thermal conductivity is a very important material parameter. The declared lambda value, we can see it here, the orange one, is 0.028 watt per meter and Kelvin. This is for a sample produced by an on-site procedure. The diagram shows different insulating renderings in comparison. These ones with 70 and 80 milliwatts are these ones with polystyrene as light additive, and the other ones with between 85, 19 and 100 milliwatt are typical products with expanded perlite as light additives. The Fixit 222 is 2 to 3 times better than the traditional products and even better than polystyrene foam. The thermal conductivity is also a function of the moisture content, as it is the case for all insulating materials. That means that a high moisture content leads to a higher thermal conductivity. This diagram shows the sorption isotherm of the aerogel blaster. On the x-axis is the relative humidity, and on the y-axis is the volume-based moisture content. And we can see that until a relative humidity of 95% is the volume-based moisture content very low. Under free water saturation, this is the point here at 100%, that means that the samples are for several weeks under liquid water, is the measured volume-based moisture content over 50%. But the water does not enter the aerogel because it's hydrophobized, but instead in the binder matrix. The vapor Water vapor resistance factor mu determines the material's reluctance to water vapor pass through. And here is a small experiment from my colleague is preparing it. So I know that Per likes this experiment so much. Okay, what is this? This is the 3 centimeter of the aerogel render. This is the final, the reinforcement render with the mesh, and then the final render and painting, the typical wall like on these buildings. And now we can see here with a little bit air, we can see here there's the air goes through very easy. Can you see the bubbles here? So I don't want to press too much. Okay, so this is a small experiment to show you how it works and that it's not vapor tight. The diagram here, we can see some typical insulating materials like organic foams on the left side. There are, I think, most of the people know this, they are a little bit more tight. And the mineral-based materials like calcium silicate board or mineral wool, these aerogel fabrics and the aerogel render 2 are very water vapor open. The diagram or the picture first. The picture is a typical application of the aerogel render with a typical plastering machine. It's nothing special, but there happened something in this machine because there is a high pressure to 8 bar. And at the beginning of our research project, we saw that that has influence of the thermal conductivity. Because here on this diagram with 2, 4, 6, 8 bars, the thermal conductivity raises up. And at the beginning, the problem was that the water was pressed forcefully in the aerogel pores. And we got as a result a higher thermal conductivity. We found a solution for the problem and patented it. And this shows us the mixture C. This is this curve below at 25 millivolts. So this problem is solved. Then we are here, I heard it this morning in an old cinema, so I have a film for you. And where can I start it? Okay, so. No, it's okay, But I need. Is it here? Is it this one?
No, it's there.
No, on the black.
Which one?
In der schwarzen Fläche.
Aha.
In der schwarzen Fläche. Jetzt draufdrücken.
Okay. Another important property is the reaction to fire. This is a small test at EMPA. So this is a brick with 5 centimeters of aerogel render, and on the left side, here this is the pure aerogel render, and on the right side, this is with the reinforcement render and the final render, the same as in the old mill. Yes, and nothing happened, so you can see it here. It's 1,500, 600 degrees hot, and nothing happened, no smoke. And the test report from the EMPA Braunschweig is in Germany. They measured the system to the European standard 13501, and it says it's A2S1D0, that means A2 non-combustible, no smoke evolution and no combustible dripping. Then we heard it in the presentation of Mr. Gustafsson that what happened with the reversibility of such products. when we use them as inner insulation. And this is only a small test here, but we can see it's in general possible. And there is at the moment a research project with the Fraunhofer Institute in Germany to discuss this point with reversibility on old buildings. And you can see it here, that's me, so I'm not so strong, but I'm strong, yes, but not. It's possible to get a powder here. Preservation bodies, a reproduction of the historical appearance, and it's a mineral-based material. The historical mill at Sissach, we heard it from the 14th century. The left picture shows us the old mill in the year 2012. And on the right side, this is a photo from last December. So it looks like this, very good. And there was an external application with around about 5 centimeters of the aerogel render on a solid masonry wall. There are position of temperature and relative humidity sensors on the west facade. This is the weather side in Sissach. This is this red cross. And the external climate, this is the green cross. And also on the north facade. I want to show you later the west facade. This is an infrared image of the building. This is the south, the right one is the south facade. And we can see that the stone window linings are the thermal weak points. But they insulated it from the inside, the reveal from the inside. So the thermal bridge is not so stretched. And this one is the diagram measured from August 2012 until November 2014. And what we can see is the thin red line. This is the external temperature. And the thin green line, the external relative humidity on the west facade. And the thicker red line is the temperature beneath the aerogel render, and the light blue line is the relative humidity beneath the aerogel render. And it's between, in summer, sometimes 70–80% relative humidity. It depends from the raining a little bit. But in winter, it's in the middle between 50 and 55% relative humidity. And the calculated dew point, this is the lila curve, is always below the measured temperature. And so for me or for us is this situation, what happened beneath the aerogel render, very good. Okay, now I want to change.
Okay. Good afternoon, ladies and gentlemen. As a representative of EMPA, I want just to tell you what EMPA is, so that you know it's something similar but not identical to SINTEF here in Norway. We are a research institute which is under the board of the ETH domain. We have the Federal Department of Economic Affairs on top. This is our Minister for Economic Affairs. I want to put an emphasis on it. We are now under the Federal Department of Economic Affairs. The whole ETH domain, that is the technical high schools in Zurich and in Lausanne. You see them here. Here is ETHZ in Zurich, the UPFL in Lausanne. Here is EMPA. This is Water Chemistry Research Institute. The other one is the Paul Scherrer Institute, which is for accelerated particle physics. This one is avalanches and landscape. Our focus areas at EMPA, we have 5 focus areas, and we are most here in the sustainable built environment. So, just these 2 slides to introduce EMPA, and then I will just go on with this aerogel render. What we have done are thermohydraulic simulations of a typical Norwegian brick wall construction. We got these information about the wall from Per Jäger. You see here we have made calculations for 4 different scenarios. The first scenario is the as-is situation here. The very first one is the as-is scenario with, you see 3 big brick thicknesses, 3 bricks here with mortar in between, and then an inner and an outer render. Then we go to the first scenario, which is an application of additional 5 centimeters to the external wall, to the external side of the wall, with additional finishing here at the end. Then we have the next scenario. We reduce this 5 centimeters to 3 on the outside, but we put 2 centimeters into the inside. This is, the reason was, sometimes you don't have the possibility of putting 5 centimeters additional. You are restricted in these thicknesses. So we thought that this scenario might be also a possible scenario. And the 4th scenario is exactly the same as the second, with this single difference that it has a water repellent final render on it. And we'll see later when we do these simulations that this is a very decisive. Of course, for making a simulation, you need some boundary conditions. That means climatic data. And this is software is called WUFI. It comes from the Fraunhofer Gesellschaft in Munich, near Munich. So we have chosen here the weather of Oslo. You see here a cold weather of it's a design reference here, which has been taken here. You see here the temperature. It's an average temperature over, I think, 10 years. And below you see the air humidity, relative humidity of the air, of the external air. These are the boundary conditions we have to put on this calculation system. So then solar radiation and wind-driven rain are the other climatic conditions which you have also to take into account. So you see here the solar radiation in different directions, here the north and the south, but what is very important is the rain. And you see here that for Oslo, the main direction of facades which see the rain coming in is the southern facades. And so we have chosen a southern orientation for the calculations we have done. That means it's a worst case calculation. For indoor temperature, we just took standard indoor temperature, 20 degrees Celsius normally, and then you see here some, when the external temperature rises, also the internal temperature will rise, and there is also an indoor relative humidity, which is between 30 and 60%. So, what we are looking here is to the total water content of the wall. You see here a calculation period of the last year. This is just, you see, 1st of October 2015 to 1st of October 2016. We have just taken out the last year. We have made the calculation for 5 years because in order to get into the quasi-steady state, you have to, and because thermohydraulic moisture and heat transfer together combined is a rather slow process. You have to, in order to get the final situation, you have to calculate more than 2 years at least. So this is what we have done, and this is what we get. You see, scenario 1 is the as is, so the uninsulated pre-retrofit situation, and all the other 3 ones are the other scenarios. And it's clear that even here, already here, at the total water content of the whole construction, scenario 4 shows, especially here, where you have, this must be some rainy events, it shows a very low water uptake. Whereas the other 2, the one with a normal finishing, which is not water repellent, and the one which has 3 centimeters outside and 2 centimeters inside, do not differ very remarkably. But what is more interesting is going into the water content of the aerogel layer itself. As my colleague Thomas Stahl already told you, the lambda value depends on the water content. That means if you can avoid moisture coming in, you avoid the increase of thermal conductivity. And this is why the water content, we have here also looked at the water content of these three scenarios. The first scenario we don't have because there was no aerogel render on the first scenario, but we have the other 3 ones. And you see here, there is a reduction in, you see the scenario number 2, which is the blue one, is just 5 centimeters outside application. And if you reduce that to 3, there is a very strong increase in that 3 centimeters. You see, this is scenario 2. And by applying a water repellent final finish, you can completely avoid the uptake of water inside this inside the external aerogel layer, which is very important when you have weather conditions where you have a lot of driving rain. Here too, we have looked also at calculated, of course, temperatures beneath the insulation layer, because it's always important to know how the temperature is beneath the insulation layer, because there it will say if you have moisture problems between the insulation layer and the wall itself. So you see here again, you have for the temperature beneath it, you see the 2 scenarios, 2 and 4 are the same, because both of them have the same temperature difference. The outer water repellent layer has no influence on the temperature itself. And the scenario 3, there is, of course, a lower temperature because you have only 3 centimeters instead of 5 on the outer facade. Relative humidity at the same point. Now it's the relative humidity. Again here, you see that the relative humidity makes a difference, of course, between the scenario 2, 3, and 4. Again here, it's not only it's not a question of heat, but it's a question of moisture transfer. And we see that there is the 5 centimeters external insulation is a good one, but it's better if you have this. It's an increase if you have a layer which is water repellent on the other side. Water repellent doesn't mean watertight, just to be very correct on that. Now, we have also shown, here we have shown here the thermal transmittance coefficient U value. Normally when we speak about U value, it's a steady state U value which doesn't take into account moisture effect. It's a dry value based on calculations or on measurements in a hot box. But here, when you make a thermohydric simulation, you take also into account the influence of the moisture, because when the moisture starts to rise, the thermal conductivity rises with that. And that's why we see here the existing brick wall, when we look at U value with 80% relative humidity, is at the steady state is 1.21. If you look at the transient calculated, it's 0.92. And if you take this for 100%, we'll look now how much is the reduction, to which level it drops down. When we have these 5 centimeters plus the external, on the external side, we have a U value, a transient U value of 0.33 and 0.34. These two do not make a big change because in the steady state, because it's the sum of the insulation thickness that makes a change. But here and here too, these three at here where it's the steady state, you don't see any changes because it doesn't take into account the moisture effect. Here, when you look at the transient ones, you see the moisture effect, and it's clearly that the one which has a water repellent has a lower transient U value. That means it has less water content, and it drops to 33% of the primary value which we have put at 100. So, and here again we have now also showing here the calculated transient U value for each month. You see here we start at December 2015 until September 2020. You see that now we have 5 years, and it's clear that the U value changes with the month depending on how wet and how cold the different months were and how much water was taken up. And you see again, of course, the best one is the one with this 5 centimeters external plus this water repellent render in most of the months. Okay, thank you very much for your kind attention. There is one point I want to add to this. What I showed you is a simulation, and a simulation is a simulation, and this is not reality as it will happen. The reality might be much more complex, but a simulation based on values that you have measured in the laboratory and put together gives you an idea how it is going to be in reality. And here, I think that the best way to find it out is to have a demonstration object here somewhere in Oslo or in southern Norway, with the collaboration of SINTEF and Riks Antikvaren, to have a real monitored object where we can really verify and optimize these findings that we have done just by simulation. Thank you.
Thank you so much.